Hello class. Today we're going to look at modeling with exponential functions. As the title goes, we've actually looked at this briefly when we started talking about exponential functions. So this video will kind of go through what we've already done before, look at some new materials such as exponential growth, dealing with relative growth rate, look at radioactive decay, and then look at what we call Newton's law of cooling. So let's do a little recap. So we discovered that every exponential function can be modeled after ab to the x. And then when we started talking about compound interest, we discovered this beautiful definition over here, a equal to p times 1 plus r all raised to the t, which happens to be our compound interest definition. And we saw that r was what we call the growth rate, and if you had 1 plus r, which was the growth factor at which p is growing, we're able to come up with that definition. And then we also looked at compounding continuously as a way of defining exponential growth of a particle or amount that you're invested in the bank. And in that case, R was not the same as what we know from above. We called R the relative growth rate. And in that case, we used what? PERT. Amount was equal to P, E raised to the RT. So we've seen this concept play out when we talked about compound interest. If we're doing it semi-annually, daily, quarterly versus when we're doing continuously. So those are the two big themes that came out. We knew this when you're compounding in a specific time period, whereas continuously meant that every moment, every instant, you were what? You were compounding your amount that you had at the bank. Okay, so let's do a little recap. All right, let's look at just an intuitive way to see how exponential growth works. So suppose you have a single bacterium and every hour it divides itself. We can see that the growth of that bacteria is going to grow exponentially. So if you look at the petri dish that I have over here, when you have just one substance divides itself in the first hour, you have two. And then the two will also divide itself after every hour. After the hour, you end up with four. And then after 3 hours, those four split, each of them are going to split up into what? Into two. So you end up getting eight. So you can clearly see that we can model that growth, that bacterial growth, by what? F of what? F of t is equal to 2 to the t. So if I look at t at 1, after the first hour, I get 2. In the second hour, I get 2 squared, which is 4, in that manner. All right. So this is called the doubling time. So if my growth factor is 2, is doubling every hour, then I can see how that equation would look like. So let's look at this example that we have over here. It says that if we start off with 10 of these bacteria, then how do I model the same thing if it's doubling every hour? Then it looks like f of x is equal to a b to the x, where a looks like my initial amount, and then it's doubling every hour, so that's 2 to the what? Raised to the t. Okay, but if we change it a little bit and say, okay, now it's not doubling every hour but doubling every 3 hours, then we can use this definition anymore. We need to adjust this definition that I put up over here. That you need to see that after every hour, it takes 3 hours for this amount to what, to double. So if I start off with 10, in 3 hours time it should be 20. So can you imagine what the expression would look like for 1 hour? So for 1 hour it's gonna be what, 2 to the 1/3. In the second hour it's gonna be 2 to the 2/3. In the third hour it's gonna be what, 2 to the what, 3/3. It seems like I need to adjust the power to allow me to accommodate for how this is doubling every 3 hours. So in that case, this becomes the expression that it's 10, my initial amount, times that growth factor that I have, raised to t over what, 3, because we're saying that it will double after every 3 hours. So it has to be t divided by 3. All right. So we have this general definition over here that if you have a doubling time, if you have an initial size that we're going to call n naught, and a doubling time of a, so I tell you the time it takes for that substance to double, then we're going to come up with this generic definition over here, that n of t is equal to the initial times the doubling factor raised to t over the doubling time. Okay. And this could change. So let's look at the problem of it. I mean, our growth factor could be different. It could be a different base. In this case, we're using base 2, doubling twice. We could use doubling, tripling. We could use any base that we want. So let's look at the example that we have over here. It says that find a model for the bacteria population after t hours. So if we read the question, it says in an ideal condition, a certain bacteria population doubles every 3 hours. So I know the growth factor is 2. All right. So A will look like P of T is equal to my initial, which is 1,000, times 2, and it's every 3 hours, so it will be T raised over 3. All right, so that would be that. And then B says, how many bacteria are in the colony after 15 hours? So what is P of 15? So that would be 1,000 times 2, 15 over 3, which is equal to 1,000 times 2 to the what? 2 to the 5th. Okay. And C is asking, how many hours will the bacteria reach 100,000? So I'm looking at 100,000 is equal to my initial, which was 1,000, to t over 3. Okay. So now our job is to kind of solve this. So I end up with 100 is equal to 2 to the t over 3. Okay. At this point, what I'm trying to solve, t, is an exponent, which is the variable that I'm trying to solve. So in my mind, I'm going, well, what notation allows me to work with variables that are powers? Well, logarithms. So I got to switch this to a logarithm. So this is going to be log base 2 of 100 is equal to what? T over 3. And so I can write this, if I do a change of base, I'm going to get log 100 divided by log 2 is equal to t over 3. And then I can get 3 log 100 all over log 2 is equal to t. Log 100, we already know what that is. That is 2, so I get 6 over log 2 is equal to t. If I pick my calculator to calculate that, log 2, I end up getting 19.93 hours. Okay. All right, let's see what they did. So they did about the same thing as I did over here. So that checks off. You end up with that definition where you have 1,000 times 2 to the t over 3. If you plug that in, you end up with that. And for C, when you try to solve for t, you end up getting approximately the same thing, 19.93 hours. So close to about 20 hours for you to get to 100,000 in the bacteria of the bacteria. Okay. All right. So this is no news to us. We've done this before, and hopefully this was a quick review for you. Now let's look at the situation where we have a relative growth rate. Remember that relative growth rate in our previous experience, we encountered this when we're doing compounding continuously, which was P is equal to, well, not amount, is equal to P e to the RT, which is what we call PERT. So let's see how we incorporate this into our exponential growth models. So based on what we just did, we can see that when we did doubling time, we had an initial amount and we had our growth factor, which was in this case doubling, and then we had a raise to the what? Raise to the t. We could have also said the same case if we were tripling. You have a tripling time. This could have been p to the 3 raised to the t. So in fact, we could realize that this is looking like a base. It's an exponential function. And it's got a base. In this case, the base is 2 for that. And in the second example where I have a tripling time, the base is 3. So we could eventually see that we could use any base that we want. But if we use a base E, when we're dealing with the population, which is modeled in terms of its relative growth rate, then it's the same as the equation that we came up with when we're dealing with compounding continuously. Because that's the only place where if we're using base E and we're dealing with the population model in terms of that, then we can say that the amount is the same as P E to the RT, where in this case our base is E and the R represents the relative growth rate. Right. So even though this was used to solve compounding continuously, we can take that approach and transfer it to when we're dealing with population that deals with the relative growth rate. All right. So we say that R is what we're calling the relative growth rate because we are calculating that population at every moment, just as we did with compounding continuously. We're compounding every millisecond, every second. When we see a relative growth rate in our population model, what we are trying to say is that at every instant, we are able to calculate what the population. So let's look at an example. I think it works best if we do an example. So let's look at the definition that we're going to use. If a population experiences exponential growth increasing according to the model, then we're going to use this definition over here. It doesn't really matter if you use n and n naught. You can clearly see this is synonymous to amount is equal to P e to the what? E to the RT. So we're just making the notations nicer for us so that we can talk about NT, and N naught is the initial. Right here is the initial population. NT is the population at any time, and R is the relative growth rate, which is expressed as the proportion of the population, and T is your time. Okay, so let's look at this example over here. It says that initial bacterium count in a culture is 500. So this is my initial population. A biologist later makes a sample count of the bacteria in the culture and finds that the relative growth rate is 40%. So we know R is 40%. Find a function that models this bacteria after t seconds. So here they didn't really tell us about any growth factor. All they told us was the relative growth rate. So I cannot model it after f of x is equal to ab to the x. I have to go use PERT. All right, I have to go use the PERT expression because it tells me about the relative growth rate, which is amount is equal to p e to the rt. So to solve A, I know that my initial amount is, so I'm going to use P because it's a population problem. So P of T is equal to 500 times E, and they tell us that is 40%, so that's 0.4 to the T raised to the T, 0.4 T. All right, so that becomes the equation. And then B says estimate the count after 10 hours. So after 10 hours, you have P of 10 is equal to 500 e to the 0.4 times 10. That gives me 500 e to the 4. Okay. And then C says, after how many hours would the bacteria reach 80,000? So I'm looking at 80,000 is equal to 500 e to the 0.4 t. Cancel out these two. And then 5 reduces this to 160. So I end up with 160 is equal to e to the 0.4 t. Again, I have the option to apply some of my properties and laws of logarithms because what I'm trying to solve is a variable. Well, the variable that I'm trying to solve is a power. So if I apply my natural logs, I get ln e to the 0.4 t. That gives me ln 160 is equal to 0.4 t ln e. Ln e is 1, so I can solve this now. Over 0.4 should be equal to t. So in this case, if I try to plug that into my calculator, divided by 0.4, I end up getting about 12.68. So it's roughly 13 hours. If you're looking at it as a whole number, you can clearly leave it as 12.68. And then it says sketch the graph of this function here. So we know that it's an exponential function. So we know it's growing, all right? So we know the shape. At time t equal to 0, there were 500 in the culture. So if this represents the 500 mark, and so it's going to grow exponentially. And we know that at 10, I have this to be 10, we have the point e to the 4. Okay. All right. So that's a quick example. And actually solve it over here too. Didn't see that. All right. So you set it up nicely. You find n of 10. And then you solve for t. You end up getting about the same thing as I had too. Okay. All right, and then that's what the graph looks like. So it's growing exponentially. We know the behavior, and we already had 2 point. We had 1 over there, and then this is up to 6. So if we look at 10, so this graph grows exponentially at 10. Somewhere here. All right, so it's not that hard to sketch the graph because you already know what the exponential graph looks like if it's growing exponentially versus decaying or decreasing. Okay. All right. So I'm going to end this for now, and we'll continue looking at radioactive decay and then Newton's law of cooling. And that would be it for applications dealing with exponential functions.